Okay, today we're going to look at section 7.2, permutations. Things such as swimming events are some of the most popular events at the Summer Olympic Games. In the finals of each event, 8 swimmers compete at the same time, making for some exciting finishes. How many different orders of finish are possible in these events? In this section, we'll extend the multiplication rule for counting to help answer questions like this one, which relate to permutations. Permutation is an ordered list of objects taken from a given population. The link to the list is given, and the list cannot contain any repeated items. So unlike the ID example we had before, we cannot have repeatings. So we're going to apply the multiplication rule for counting permutations. In the case of the swimming finals, one possible permutation of link 3 would be the list of medal winners, first, second, and third place finishers. Permutation of length 8 would be the full order finish, first through 8th place. Let's use the multiplication rule for counting to figure out how many each of these permutations there are. So you have a hand of 5 cards. It happens to create what's called a royal flush in the game of poker. And how many different orders can we put those cards? So we're just looking at these 5 cards. 10 of spades, jack of spades, queen of spades, king of spades, ace of spades. So I have these 5 cards. How many different ways can I put them in order? Keeping in mind, there are no repeats. So my first card can be any of them, right? So there's 5 possibilities for the first card. So let's say the first card was the ace. Now, how many possibilities do I have for the second card? Well, of course, there's 4. Now, let's say the second card was the 10 of spades. Doesn't really matter what it was, but to make this easier to see. So how many possibilities are there for the third card? Well, there's only 3. And maybe that was the queen of spades. And how many possibilities are there for the second card? Well, there's only 2. And that was the king. And lastly, 1. And now using our multiplication rule of counting, multiply all of these together. And there's 120 ways to get those 5 cards. Now, keeping in mind the order didn't matter, but there could not be repeats. And the next thing we look at here is called a factorial. You may have heard of this. The pattern we see in the previous example occurs commonly enough that we have a name for it, factorial. For any positive number n, we define a factorial of n, denoted n with a explanation point, read n factorial, to be the product of every whole number less than or equal to n. We also define 0 factorial to be equal to 1. We will use factorials in a couple of different contexts. So let's get some practice doing these computations. So we start out with 6 factorial. Well, this is simply 6 times 5 times 4 times 3 times 2 times 1, which would be 720. Okay, now we have 12 factorial divided by 10 factorial. Well, this would be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all divided by 10 factorial, which is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, the interesting thing about this division in this case, remember, you can divide out common factors in the numerator and denominator. So if some factor is in the numerator and in the denominator, we can divide them out. And I have 10 times 9 times 8 all the way to 1 and 10 times 9 times 8. So this is essentially 12 times 11, which is 132. Okay, so let's look at this one. This is 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 4 factorial, 4 times 3 times 2 times 1 times 4 factorial, 4 times 3 times 2 times 1. This and this cancels out. 4 times 3 times 2 times 1 is 24. 8 times 7 times 6 times 5 is 1,680. Divide by the 24, and I get 70. And that's how this works. So now we get to permutations. As we've seen, factorials can pop up when we're computing permutations. In fact, there's a formula we can use to make that connection explicit. So let's define some notations first. If we have a collection of n objects, and we wish to create an ordered list of R objects, where R is between 1 and n inclusive, call the number of those permutations NPR, read as the number of permutations of n objects taking R at a time. We can formalize this formula. We'll use this to compute permutations. This is it. This is the formula I need. So the number of ways I can take R from n objects, the number of permutations, is n factorial divided by n minus R factorial. So let's do some examples here. The number of permutations of 6 objects taken 2 at a time. So n equals 6 and R equals 2. So 6, 2, P2 equals 6 factorial over 6 minus 2 factorial. 6 factorial over 4 factorial. And 6 factorial is simply 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial is 4 times 3 times 2 times 1. This and this cancel out, and I end up with 30. Okay? Look at another one here. The number of permutations of 14 objects taken 4 at a time. So n is 14, R is 4. So 14 objects taken 4 at a time is 14 factorial over 14 minus 4 factorial is 14 factorial over 10 factorial. Now, we can cut down on writing. 14 times 13 times 12 times 11 times 10 factorial over 10 factorial. And this cancels that. And I end up with 14 times 13 times 12 times 11, or 24,024. Okay, let's look at another one here. Number of permutations of 19 objects taken 3 at a time. N equals 19, R equals 3. 19 objects, number of permutations of 19 objects taken 3 at a time. 19 factorial over 19 minus 3 factorial. 19 factorial over 16 factorial. 19 times 18 times 17 times 16 factorial over 16 factorial. 16 factorials cancel out, and I end up with 19 times 18 times 17. 5,814. One of the big draws at this year's state fair is the pig race. There are 15 entrants, and prizes are given for the top 3 finishers. How many different combinations of top three finishes could there be? N equals 15. R equals 3. So we're looking at 15 pigs, taking 3 at a time. 15 factorial over 15 minus 3 factorial. 15 factorial over 12 factorial. 15 times 14 times 13 times 12 factorial over 12 factorial. So the 12 factorials cancel out. And I end up at 15 times 14 times 13 or 2,730. And that's how it works. Now notice something with this pig race or the swimming meet. With permutations, the order matters. So if my finish is pig 1, 2, and 3, that is not the same as pig 2, 1, and 3. That's not the same finishing order. So in permutations, order matters. That's very important to remember. And that finishes up our permutation section.